Every time you look at the night sky, you are not seeing the present, you are seeing the past. The light from the moon left the lunar surface about 1.3 seconds ago. At the speed of light, which is approximately 300,000 kilometers per second, the moon is close enough that this delay is barely perceptible, a heartbeat of cosmic time. The light from the sun is 8 minutes and 20 seconds old by the time it reaches your eyes. When you see the sun rise over the horizon, the nuclear reactions that produce the light you are observing happened before your morning coffee began to cool. The light from the nearest star beyond our sun, Proxima Centauri, is 4 years and 3 months old. The light from Sirius, the brightest star in the night sky, is 8.6 years old. When you look at Sirius, you are seeing the star as it was in the mid-2010s. The light from Betelgeuse, the bright red star at the shoulder of Orion, left that star about 700 years ago, when the Black Death was still a fresh memory in Europe and the Ming Dynasty was newly established in China. If Betelgeuse exploded tonight, which it may have already, since it is expected to go supernova within the next 100,000 years, we would not see the explosion for 700 years. The night sky is a museum of ancient light. The Andromeda Galaxy, the nearest large galaxy to the Milky Way, is visible on a clear dark night as a faint smear of light slightly larger than the full moon. The light reaching your eyes when you observe Andromeda left that galaxy 2.5 million years ago. At that moment in Earth's history, the ancestors of modern humans were Australopithecus, small-brained stone tool using hominids who had not yet developed the controlled use of fire. The universe you are looking at is not the universe as it is. It is the universe as it was, at many different moments in time, all displayed simultaneously across the night sky. The most distant objects visible in the deepest telescope images emitted the light we observe more than 13 billion years ago, when the universe was only a few 100 million years old, when the first galaxies were just beginning to coalesce from the primordial gas clouds of the Big Bang. The universe is so large that looking across it in space is simultaneously looking back in time. The entire observable universe is a time machine with no moving parts. Tonight we rest in the universe, not the familiar scale of houses and cities and countries, not even the scale of the solar system or the galaxy, but the full, staggering, incomprehensible scale of the universe itself, its history, its contents, its laws, its mysteries, and the extraordinary improbability of consciousness arising within it to observe it. Every fact in this long, quiet night of science is real. Every number, every distance, every age is the best estimate of the best scientists who have ever studied these questions. Take a slow, full breath in, all the way, gently, until your lungs cannot comfortably hold anymore. Hold it for just a moment, and now breathe out, long and slow and complete, feeling your body soften as the air leaves. Let your weight settle fully into whatever is beneath you. Let your muscles release, one by one. There is nothing you need to do tonight. The universe has been running for 13.8 billion years and will continue running whether or not you attend to it. Your only task is to breathe, and then to rest, and eventually to sleep. The universe is estimated to contain approximately 2 trillion galaxies within the observable region, though the count was revised upward dramatically in 2016 from a previous estimate of about 200 billion when researchers applied new correction factors for galaxies too faint and too distant to observe directly. Each of those 2 trillion galaxies contains anywhere from a few million to several trillion stars, depending on its size. Our own Milky Way has somewhere between 100 and 400 billion stars. A conservative estimate for the total number of stars in the observable universe is about 200 sextillion, which is written as a 2 followed by 23 zeros. 200,000 billion stars. If you could count stars at the rate of 1 per second without sleeping, it would take you about 6 trillion years to count them all, more than 400 times the current age of the universe. Each of those stars is in many respects similar to our Sun. Each is a ball of plasma undergoing nuclear fusion in its core, maintained in hydrostatic equilibrium between the inward pull of its gravity and the outward pressure of its hot interior. Each has spent millions to billions of years converting hydrogen into helium in its core, releasing energy in the form of photons that take tens of thousands of years to reach the surface of the star from which they finally escape as light. Many of those stars have planets. Many of those planets orbit at distances where liquid water could exist on the surface. Some of those planets have been doing so for billions of years. And yet, as far as we know, only one of those planets has produced life. Only one has been confirmed to have oceans and continents and an oxygen atmosphere and billions of species of living organisms, and one particular species of primate that has developed language, mathematics, science, and space telescopes capable of imaging the first galaxies. Whether this is a reflection of the extraordinary rarity of life, or whether life is common and we simply have not yet detected it elsewhere, is one of the greatest unanswered questions in science. But even if life were extraordinarily rare, the sheer number of candidate locations, potentially hundreds of billions of habitable planets in the Milky Way alone, means that the probability of life elsewhere is high, even if the rate of origin is very low. Let your breathing settle and slow. The universe is going about its ancient business tonight. Stars are being born in molecular clouds in galaxies across the cosmos. Stars are dying in supernovae, briefly outshining their entire host galaxies. Black holes are pulling in gas and dust, and occasionally companion stars. The cosmic microwave background radiation, the afterglow of the Big Bang, is filling all of space with its ancient cooling light, and here you are, in a warm room, on a planet, in a solar system, in a galaxy, in the middle of it all. The observable universe, the region from which light has had time to reach us in the 8 billion years since the Big Bang, has a radius of about 46.5 billion light years. This is larger than 13.8 billion light years, which you might expect to be the limit, because the universe has been expanding during all that time, so the regions from which the most ancient light departed are now much farther away than they were when they emitted that light. The observable universe is therefore a sphere about 93 billion light years in diameter, containing those 2 trillion galaxies and their 200 sextillion stars. But the observable universe is not the whole universe. It is merely the portion we can observe. The actual universe may be much larger, possibly infinite. Measurements of the cosmic microwave background show that the universe is geometrically flat to to high precision, meaning that the geometry of space is not curved back on itself into a finite sphere or saddle shape, but is flat like a Euclidean space, which is consistent with an infinite, or at least enormously large universe, extending far beyond what we can observe. We do not know how much larger the universe is beyond our observable horizon. It may be 10 times larger, or 100 times, or 1,000,000,000,000 times, or it may be truly infinite, extending without limit in every direction. We cannot know, because the light from those distant regions has not had time to reach us. Light is the fastest possible signal in the universe. Einstein's special relativity establishes that nothing with mass can be accelerated to the speed of light, and that only massless particles, like photons, can travel at exactly the speed of light. This means there is a fundamental limit to how quickly information can travel through the universe, and this limit is the speed of light. The observable universe is defined by this limit. Beyond the cosmic horizon, events can occur that we will never know about, because their light can never reach us. As the universe expands under the influence of dark energy, this horizon is gradually becoming smaller relative to the total universe, meaning that distant galaxies are eventually receding away from us faster than light can cross the growing distance, making them permanently unreachable and eventually unobservable. Light itself is a remarkable phenomenon. It is an electromagnetic wave, a coupled oscillation of electric and magnetic fields propagating through space at 297,92,458 meters per second. Visible light, the portion of the electromagnetic spectrum that human eyes are sensitive to, occupies a narrow band of wavelengths between about 380 nanometers, which appears violet, to about 700 nanometers, which appears red. But the electromagnetic spectrum extends far beyond visible light in both directions. Gamma rays, the most energetic, have wavelengths smaller than an atomic nucleus. X-rays are used in medical imaging. Ultraviolet light causes sunburn. Infrared light is felt as heat and is used in night vision technology. Microwaves heat food and transmit wireless communications. Radio waves, with wavelengths from centimeters to kilometers, carry television and radio broadcasts. The universe is brilliantly active across the entire electromagnetic spectrum. Stars like the sun emit most of their energy as visible light and near-infrared radiation. Hot young blue stars emit strongly in ultraviolet. Neutron stars and black hole accretion disks emit X-rays. Supernova remnants and certain galaxies emit radio waves. Gamma ray bursts, the most energetic individual events in the universe, release more energy in a few seconds than the sun will radiate in its entire 10 billion year lifetime, all as gamma rays. Human eyes are tuned to visible light because the sun emits most of its energy there, and the atmosphere of Earth is most transparent to those wavelengths, but the universe is far richer and stranger in the wavelengths we cannot see than in the ones we can. The expansion of the universe was discovered by Edwin Hubble in the 1920s. Hubble measured the distances to nearby galaxies using Cepheid variable stars and compared those distances to the redshifts of the galaxies, the stretching of their light toward longer, redder wavelengths caused by their motion away from us. He found that virtually all galaxies were redshifted, moving away from us, and that the more distant they were, the faster they were receding. This relationship, now called Hubble's law, implied that the universe was expanding. Every galaxy is moving away from every other galaxy, not because they are flying through space, but because the space between them is stretching. The analogy is often made to dots on a balloon being inflated. Every dot moves away from every other dot as the balloon expands. And dots that are farther apart move apart faster because more rubber stretches between them. Hubble's discovery implied that the universe had a beginning, a moment in the past, when all the matter and energy of the observable universe was compressed into an extraordinarily small, hot, dense state. Running the expansion backward in time leads to a moment of origin about 13.8 billion years ago. This is the Big Bang. The term was actually coined mockingly by the astronomer Fred Hoyle, who preferred a rival steady-state model of the universe in which matter was continuously created and the universe had no beginning. But the evidence for the Big Bang, particularly the discovery of the cosmic microwave background radiation in 1965, firmly established the expanding universe model. Let your breath slow a little more. In and out. The universe is expanding around you at this moment, imperceptibly slowly at the scale of the solar system, but cumulatively significant over the billions of light years between galaxy clusters. The expansion is not something you can feel or detect in everyday life. It operates at scales that dwarf anything in human experience. But it is real, and it has been running since the Big Bang. In 1998, two teams of astronomers studying distant Type 1 supernovae, which are used as standard candles for measuring cosmic distances, independently discovered that the expansion of the universe is accelerating. They expected to find that gravity was slowing the expansion, gradually decelerating it as the mutual gravitational attraction of all the matter in the universe pulled back against the outward momentum of the Big Bang. Instead, they found the opposite. The most distant supernovae were dimmer than expected, meaning they were farther away than expected. Meaning the universe had been expanding faster in the recent past than in the more distant past. The expansion was speeding up. The leaders of the two teams, Saul Perlmutter, Brian Schmidt, and Adam Ries, received the Nobel Prize in Physics in 2011 for this discovery. The cause of the accelerating expansion is attributed to what is called dark energy, a term for whatever component of the universe is driving this acceleration. Dark energy makes up approximately 68% of the total energy content of the universe, according to the best current measurements. Ordinary matter, the kind made of protons, neutrons, and electrons that makes up stars, planets, and people, accounts for only about 5% of the universe's energy content. Dark matter accounts for about 27%. Dark energy is 68%. So the vast majority of the universe, about 95%, is in forms we cannot directly observe, only infer through their gravitational and other effects. The universe is profoundly strange and largely opaque to our direct instruments. Dark energy may be a property of space itself, what Einstein called the cosmological constant, an energy density inherent to empty space that remains constant as the universe expands. If the energy density of dark energy is truly constant, the expansion of the universe will continue accelerating forever. Galaxies will eventually disappear beyond our observable horizon, and the universe will grow cold and dark and empty over incomprehensible timescales. An alternative possibility is that dark energy is a dynamic field that changes over time, perhaps eventually reversing and causing the universe to recollapse in a big crunch, or perhaps causing the expansion to accelerate so rapidly that even atoms are torn apart in a final catastrophe called the Big Rip. We do not currently have the observational precision to distinguish between these possibilities. The nature of dark energy is one of the most important unsolved problems in all of physics. Dark matter, the other great mystery of the cosmos, is the name given to the invisible mass that is required to explain the rotation of galaxies, the motion of galaxies in clusters, the large-scale structure of the universe, and the details of the cosmic microwave background. As we discussed when exploring galaxies, the rotation curves of spiral galaxies are flat when they should decline at large distances from the center, implying there is additional invisible mass and a large halo around each galaxy. The total amount of dark matter inferred from these observations and confirmed by independent lines of evidence is about 5 times the amount of ordinary matter. We do not know what dark matter is. It does not emit, absorb, or scatter light, making it invisible to all our telescopes. It interacts with ordinary matter only through gravity and possibly through the weak nuclear force. The leading candidate for many years was a class of hypothetical particles called WIMPs, weakly interacting massive particles, which arise naturally in certain extensions of the standard model of particle physics. But decades of sensitive experiments searching for WIMP interactions with detector materials have found no convincing signal. Other candidates include sterile neutrinos, axions, primordial black holes formed in the very early universe, and entirely new types of matter not predicted by any current theory. The nature of dark matter, like that of dark energy, remains one of the central mysteries of modern science. Neutron stars are among the most extreme physical objects in the universe. They form when a massive star, typically between about 8 and 20 times the mass of the Sun, exhausts its nuclear fuel and collapses. The outer layers are blasted away in a supernova explosion. The core collapses under gravity so intensely that protons and electrons are forced together to form neutrons. The result is a ball of neutrons about 20 kilometers in diameter, roughly the size of a city, but containing about 1.4 times the mass of the Sun. The density of a neutron star is almost incomprehensibly high. A teaspoonful of neutron star material would weigh about 900 times the mass of the Great Pyramid of Giza on Earth's surface. The gravitational field at the surface of a neutron star is about 200 billion times stronger than Earth's gravitational field. A 70-kilogram person standing on the surface of a neutron star would weigh about 14 trillion kilograms, equivalent to the weight of a small mountain on Earth. The speed required to escape the surface is about 0.3 to 0.7 times the speed of light. The equations of general relativity must be used to accurately describe the physics at the surface of a neutron star, because Newtonian gravity is not sufficient. Pulsars are rapidly rotating neutron stars that emit beams of radio waves or other electromagnetic radiation from their magnetic poles. As the neutron star rotates, the beams sweep across space like lighthouse beams. And if Earth happens to be in the path of the beam, we detect a pulse of radiation with each rotation. Pulsars rotate at rates ranging from about 1 rotation per second for ordinary pulsars to hundreds of rotations per second for the fastest millisecond pulsars. The fastest known pulsar, PSR J1 Centene 482446A, rotates 716 times per second. It is spinning so fast that its equator is moving at about 24% of the speed of light. Pulsar timing is one of the most precise measurements in physics. The rotation of a pulsar is extraordinarily stable, like an extremely accurate clock, and deviations from the expected timing can be used to detect the effects of general relativity, the presence of companion stars or planets, and even gravitational waves passing through the pulsar. The first confirmed exoplanets were actually discovered in 1992 by the detection of timing anomalies in the pulsar PSR 157+12, before the first planets around a sun-like star were found in 1995. Magnetars are a subtype of neutron star with extraordinarily powerful magnetic fields, up to about 1,000 trillion times stronger than Earth's magnetic field. They are the most magnetically intense objects known to exist. A magnetar at the distance of the moon would wipe all credit card data on Earth and would be lethal to life at ranges of about 1,000 kilometers due to its effects on biological chemistry. Fortunately, the nearest known magnetar is about 9,000 light-years away. Magnetars occasionally release enormous bursts of energy called soft gamma-ray repeater events, which are among the most energetic events in the universe short of supernovae and gamma-ray bursts. Let your breathing settle into a slow, comfortable rhythm. The neutron stars and magnetars are far away, spinning in the dark. The universe accommodates extraordinary violence and extraordinary calm simultaneously in different places. Here, in this room, on this planet, everything is still. The life cycle of a star is one of the most complete and well-understood stories in science. A star begins in a molecular cloud, a cold, dense region of the interstellar medium where gas and dust have accumulated to sufficient density for gravity to cause collapse. As the cloud collapses, it heats up through the conversion of gravitational potential energy to thermal energy. It also spins faster as it contracts, conserving angular momentum. And the rotating cloud flattens into a disk with a central concentration of mass that grows toward stellar conditions. When the core temperature reaches about 10 million degrees Celsius, hydrogen fusion ignites and the star begins to shine. The duration of a star's life on the main sequence, the period of stable hydrogen burning, depends critically on its mass. Massive stars burn hot and fast, consuming their hydrogen supply in only a few million years. A star of 10 solar masses lives for about 30 million years. A star of 20 solar masses lives for only about 8 million years. The most massive stars known, some of them more than 100 times the mass of the Sun, live for only a few million years at most. Our Sun, at 1 solar mass, has a main sequence lifetime of about 10 billion years, of which it is currently about halfway through. At the other end of the mass spectrum, red dwarf stars, with masses between about 0.08 and 0, 5 solar masses, burn their hydrogen so slowly and so thoroughly that they can live for tens to hundreds of billions of years. The least massive red dwarfs will live for more than 10 trillion years, nearly 1,000 times the current age of the universe. Not a single red dwarf star has ever died in the history of the universe, because none has yet run out of fuel. They are the silent, patient majority of the stellar population, far outnumbering sun-like stars, living lives of quiet efficiency in the darkness between brighter stars. When a star like the Sun exhausts the hydrogen in its core, it expands into a red giant. The core contracts and heats up, while the outer layers expand dramatically, cooling to a deep red as they thin and spread. The Sun will eventually expand to perhaps 200 times its current diameter. In its red giant phase, it may reach or even slightly exceed Earth's current orbital radius, though whether Earth will be swallowed depends on mass loss rates during the red giant phase. Eventually, the Sun's core will become hot enough to ignite helium fusion, which produces carbon and oxygen. When the helium is exhausted, the Sun will not have sufficient mass to fuse carbon, and the core will contract into a white dwarf, while the outer layers are expelled in a glowing shell called a planetary nebula, creating a beautiful, short-lived structure of ionized gas surrounding the dying stellar remnant. White dwarfs are the most common stellar endpoint in the universe. They are the dense, hot remnants of low to medium mass stars after they have shed their outer layers. A typical white dwarf has about 0.6 solar masses, compressed into a sphere about the size of Earth, an average density about 200,000 times that of water. White dwarfs are supported not by thermal pressure or nuclear fusion, but by electron degeneracy pressure, a quantum mechanical effect that prevents electrons from occupying the same quantum state. This means they do not need to continue burning fuel to support themselves against gravity. They simply cool, very slowly, over billions to trillions of years. The Chandrasekhar limit, named after the Indian astrophysicist Subrahmanyan Chandrasekhar, who derived it in 1930 at the age of 19, is the maximum mass that a white dwarf can have and remain stable, approximately 1.4 solar masses. Above this limit, electron degeneracy pressure is insufficient to support the star against gravity, and the white dwarf collapses. If a white dwarf in a binary star system accretes mass from a companion star until it approaches the Chandrasekhar limit, it undergoes a thermonuclear explosion, a Type 1 supernova, which destroys the white dwarf entirely and releases an enormous amount of energy. Because the trigger mass is always the same Chandrasekhar limit, Type 1 supernovae have roughly the same intrinsic luminosity regardless of where they occur, making them standard candles useful for measuring cosmic distances, which is how the accelerating expansion of the universe was discovered. White dwarfs cool so slowly that no white dwarf has yet cooled to become a black dwarf, a hypothetical cold, dark stellar remnant that would emit no radiation and be essentially invisible. The universe is not yet old enough for any white dwarf to have cooled all the way. The coolest white dwarfs known have temperatures of only a few thousand degrees, still glowing faintly white. In the far future, tens of billions to trillions of years from now, white dwarfs will finally cool to become black dwarfs, cold and dark and scattered throughout the galaxy, the silent memorial to the stars that once blazed. Nebulae, the gaseous clouds of the interstellar medium, come in many forms and serve many roles in the life cycle of stellar material. Emission nebulae are clouds of ionized gas that glow with their own light excited by the ultraviolet radiation of nearby hot young stars. The most famous emission nebula is the Orion Nebula, M42, visible to the naked eye as the fuzzy middle star of Orion's sword, a vast star-forming region about 1,344 light-years away, containing thousands of young stars of various ages and masses. In the depths of the Orion Nebula, astronomers have found protoplanetary disks, flattened structures of gas and dust around young stars where planets are currently forming, providing direct visual evidence of the planet formation process. Reflection nebulae are clouds of gas and dust that do not produce their own light, but instead reflect the light of nearby stars. They are typically blue in color because dust grains scatter blue light more efficiently than red, the same reason Earth's sky is blue. Dark nebulae are dense clouds of gas and dust that are visible not by their own light or reflected light, but by the stars they obscure, silhouetted against brighter background regions. The Horsehead Nebula in Orion is a famous example of a dark nebula, its distinctive shape formed by the dense cloud projecting into a brighter emission nebula behind it. Planetary nebulae, despite their name having nothing to do with planets, are shells of gas expelled by dying stars of low to intermediate mass. They were named by William Herschel in the 18th century because many of them appeared as small, round green-tinted disks through the telescopes of the time, superficially resembling the disk of a planet like Uranus. Planetary nebulae are among the most beautiful objects in the universe, their various symmetrical shapes and colors produced by the complex ejection history of the dying star, the illumination pattern of the hot white dwarf at the center, and the chemical composition of the expelled gas. The Helix Nebula, the Ring Nebula, the Butterfly Nebula, and the Cat's Eye Nebula are examples of the extraordinary diversity of planetary nebula morphology. The interstellar medium, the gas and dust that fills the space between stars within a galaxy, is not a uniform distribution of material. It is a dynamic, multi-phase system in a state of continuous exchange with the stars embedded within it. Stars form from dense, cold regions of the interstellar medium, particularly molecular clouds. When stars die, they return their material to the interstellar medium through stellar winds, planetary nebulae, and supernova explosions, enriching it with the heavy elements they have synthesized during their lives. The next generation of stars forms from this enriched material, incorporating the carbon and oxygen and iron and all the other elements that previous generations of stars produced. The interstellar medium is the medium of cosmic recycling, the highway through which matter passes on its way from one stellar incarnation to the next. Your body is made of material that has been through this cycle many times. The atoms in your body were last part of a star, or more likely multiple different stars in succession, before they were incorporated into the solar nebula 4. 6 billion years ago, and eventually ended up in the planet and the ocean and the atmosphere and the food chain that assembled you from them over billions of years. The iron in your hemoglobin was made in the core of a massive star that exploded in a supernova before the sun formed. The calcium in your bones was made in the helium burning shell of a red giant star. The oxygen you are breathing was produced partly in stellar nucleosynthesis and partly by 2.5 billion years of photosynthesis by organisms living in the ancient ocean of early Earth. You are made of the universe's own material, assembled in you by biological processes. Let your breath be steady and slow. In, gently. Out, completely. Let your body rest. The universe made you from stardust, assembled you with extraordinary complexity, and right now you are resting in it, as part of it. That is not a metaphor. It is chemistry and physics. The search for extraterrestrial life is one of the most profound scientific endeavors of our time. It addresses the question of whether the chemistry and processes that gave rise to life on Earth are common throughout the universe, or whether life on Earth is a singular, isolated event. The discovery of life beyond Earth would be one of the most significant scientific findings in human history, with implications for our understanding of biology, chemistry, cosmology, and the place of consciousness in the universe. The simplest and most fundamental argument for the commonality of life is the argument from numbers. There are at least 200 billion galaxies in the observable universe, each containing, on average, perhaps 100 billion stars, for a total of at least 2 × 10 to the 22nd power stars. Measurements from the Kepler Space Telescope suggest that most stars have planets, and that perhaps 1 in 5 Sun-like stars has a planet in the habitable zone. Even if the probability of life arising on any given habitable planet were as low as 1 in a billion, the expected number of life-bearing planets in the observable universe would still be in the trillions. The universe is very large, and even improbable events can occur many times in a very large system. The Drake equation, formulated by radio astronomer Frank Drake in 1961 in preparation for the first SETI conference, is a formula for estimating the number of technologically advanced civilizations in the Milky Way with whom we might be able to communicate. It expresses this number as the product of 7 factors: the rate of star formation in the Milky Way, the fraction of stars with planets, the average number of potentially habitable planets per star with planets, the fraction of those planets where life actually arises, the fraction of life-bearing planets where intelligent life evolves, the fraction of intelligent civilizations that develop detectable technology, and the average lifetime of such civilizations. The first 3 factors are now reasonably well constrained by astronomical observation. The last 4, the biological and sociological factors, are deeply uncertain and span many orders of magnitude in their plausible range. The Fermi paradox, named for the physicist Enrico Fermi, who posed a version of it informally in 1950, asks if advanced civilizations are common in the galaxy. Why have we not detected any evidence of them? The Milky Way is about 10 billion years old. If civilizations commonly arise around sun-like stars, some of them would have formed billions of years before our solar system, long enough to have colonized the entire galaxy, even at speeds far less than the speed of light, using robotic probes or self-replicating machines. The absence of any detected extraterrestrial civilizations, despite increasingly sensitive searches, is called the Great Silence, and its explanation is one of the most fascinating puzzles in science. Proposed resolutions to the Fermi paradox range from the mundane to the profound. Perhaps the distances between stars are simply too large and the timescales too long for any civilization to reach us, and the galaxy is full of isolated civilizations, each unaware of the others. Perhaps civilizations tend to destroy themselves before they reach the technological stage needed for interstellar communication or travel, a possibility sometimes called the Great Filter. Perhaps we are not looking in the right way, or at the right frequencies, or with sufficient sensitivity. Perhaps advanced civilizations deliberately avoid contact with less developed ones. Perhaps we are genuinely the first or among the first technological civilizations in the galaxy, in which case the Great Filter lies ahead of us rather than behind us, which is perhaps the most unsettling possibility. The search for biosignatures, chemical or physical signs of life, in the atmospheres of exoplanets is a growing field of observational astronomy. The James Webb Space Telescope has begun characterizing the atmospheres of exoplanets by measuring how the spectrum of starlight changes when a planet passes in front of its star. The planet's atmosphere absorbs specific wavelengths of the starlight passing through it, leaving absorption features that reveal the chemical composition. Detecting molecular oxygen, ozone, methane, or nitrous oxide in the atmosphere of an Earth-like exoplanet would be highly suggestive of biological activity because these molecules are thermodynamically unstable and would quickly disappear without continuous biological replenishment. The detection of such biosignatures would not be proof of life, but it would be a powerful hint. The Milky Way is itself embedded in a larger context that provides essential backdrop to the universe's nature. Our galaxy is part of the local group, a collection of about 60 galaxies spanning about 10 million light years. Beyond the local group is the Virgo cluster, the nearest large concentration of galaxies, about 65 million light years away, containing more than 1,300 galaxies. The local group, the Virgo cluster, and dozens of other galaxy groups and clusters together form the Laniakea supercluster, spanning about 520 million light years. Laniakea is itself part of a larger structure connected by filaments of the cosmic web to neighboring superclusters, including the Perseus-Pisces supercluster and the Coma supercluster. The cosmic web is the largest scale structure of the universe, the arrangement of matter on scales of hundreds of millions to billions of light years. Galaxies and galaxy clusters are concentrated along filaments and at the nodes where filaments meet. Between the filaments are enormous voids, regions of very low galaxy density that can span hundreds of millions of light years. The cosmic web was predicted by cosmological simulations in the 1980s and confirmed by large-scale galaxy surveys in the decades since. Its origin lies in tiny quantum fluctuations in the density of the early universe that were amplified by gravity over billions of years into the structures we see today. The cosmic microwave background radiation is the oldest light in the universe. The radiation released 380,000 years after the Big Bang, when the universe had cooled enough for electrons to combine with protons and form neutral hydrogen atoms, making the universe transparent for the first time. Before this moment, called recombination, the universe was filled with a hot, opaque plasma in which light could not travel freely. At recombination, the photons that had been trapped in this plasma were suddenly able to travel freely, and they have been doing so ever since, cooling as the universe expands. Today, the cosmic microwave background has cooled to a temperature of 2.725 Kelvin, just a few degrees above absolute zero, and its photons have wavelengths in the microwave part of the spectrum. The cosmic microwave background fills all of space uniformly, arriving from every direction with almost exactly the same intensity. The tiny variations in its temperature, measured at the level of 1 part in 100,000, reflect the tiny density variations in the early universe that seeded the formation of all subsequent structure. The pattern of these temperature variations, measured with extraordinary precision by the UMAP and Planck satellite missions, encodes information about the age, composition, and geometry of the universe. It is from these measurements that we know the universe is 13.8 billion years old, that ordinary matter makes up 5% of the total energy content, that dark matter is 27%, and that dark energy is 68%. The very early universe, before the cosmic microwave background was released, is a period of extraordinary physical conditions. At the moment of the Big Bang, or more precisely at the Planck time, 10 to the power of minus 43 seconds after the bang, the temperature was approximately 10 to the power of 32 Kelvin, and the density was incomprehensibly high. The known laws of physics cease to be reliable at these conditions, because quantum effects on gravity are significant, and we do not have a complete theory of quantum gravity. In the first tiny fraction of a second after the Big Bang, the universe underwent a period of extraordinarily rapid exponential expansion called cosmic inflation. In this period, the universe expanded by at least 60 orders of magnitude, from a region smaller than an atomic nucleus to a region perhaps centimeters or meters across, in a time interval shorter than 10 to the power of minus 32 seconds. Inflation was proposed by Alan Guth in 1980 to solve several puzzles of the standard Big Bang model, including why the universe is so geometrically flat, why the cosmic microwave background is so uniform in temperature across regions that would not have been in causal contact without inflation, and why we do not observe magnetic monopolies or other exotic particles predicted by grand unified theories. Inflation elegantly solves all these problems by proposing that the observable universe grew from a single, tiny, causally connected region that was stretched to enormous size during the inflationary period, erasing any initial inhomogeneities and making the resulting space flat and uniform. Inflation also explains the origin of the density variations seen in the cosmic microwave background. During inflation, quantum fluctuations in the inflaton field, the hypothetical field driving inflation, were stretched to astronomical scales, seeding small density variations that gravity later amplified into the galaxies and large-scale structures we see today. The predictions of inflationary models for the statistical properties of these density variations match the observed properties of the cosmic microwave background with remarkable precision. Let your breath be slow and easy. The universe has been doing this for 13.8 billion years, expanding, cooling, forming structures, cycling matter through stars, and producing, in at least one place, beings who can understand the story of their own cosmic origin. The expansion continues. The cooling continues. The star formation continues. And tonight, here, everything is quiet. The nature of time in the universe is one of the most profound and counterintuitive topics in physics. Einstein's special relativity showed that time is not absolute, but relative, depending on the motion of the observer. A moving clock runs slow relative to a stationary one by a factor determined by its speed. This is not a perceptual trick or a measurement artifact. It is a real physical effect. The clocks on GPS satellites must be corrected for this time dilation, because without the correction, they would accumulate errors of about 7 microseconds per day due to special relativistic effects, which would cause GPS position errors of about 2 kilometers per day. General relativity adds another layer. Gravity also affects the passage of time. Clocks in stronger gravitational fields run slow relative to clocks in weaker gravitational fields. GPS satellites also experience this effect, running fast by about 45 microseconds per day because they are higher in Earth's gravitational field. The net effect, combining special and general relativistic corrections, is that GPS clocks must be adjusted to run at a rate slightly different from surface clocks to stay synchronized. These corrections are not exotic theoretical adjustments. They are essential engineering requirements for the GPS system to function. At the extreme of general relativistic time dilation, near the event horizon of a black hole, the effect becomes dramatic. An observer hovering close to the event horizon of a black hole, maintained at a fixed distance by an enormously powerful rocket, would experience time at a rate that approaches zero relative to a distant observer. Looking up at the distant universe, they would see it evolve and fast forward. The stars burning and dying, and new ones forming in what appears to them like an accelerated cosmic movie. Looking down at the event horizon below them, they would see nothing, because light cannot escape from beyond the horizon. If an observer were to fall freely through the event horizon of a large enough black hole, they would not immediately notice anything special at the moment of crossing. The event horizon is not a physical barrier, but a mathematical surface, and the tidal forces at the horizon of a supermassive black hole, like the one at the center of M87, are small enough that a human could cross it without immediately being torn apart. But after crossing, the future light cones of all events, the set of directions from which light can reach the observer, all point toward the singularity at the center. There is no possible path, not even a path at the speed of light, that leads away from the singularity. For the infalling observer, reaching the singularity is as inevitable as the passage of time itself. The ultimate fate of the universe on the timescales of cosmology depends on the nature of dark energy and other physical processes that will unfold far in the future. If dark energy is a cosmological constant, the expansion of the universe will continue accelerating forever. Stars will continue forming for perhaps another 100 trillion years as the remaining gas in galaxies is consumed. After the last stars die, the universe will enter the degenerate era, populated primarily by white dwarfs, neutron stars, and black holes. White dwarfs will gradually cool over quintillions of years to become black dwarfs. Neutron stars will experience internal quantum mechanical processes over even longer timescales. Black holes will dominate the far future of the universe, slowly evaporating through Hawking radiation over timescales of 10 to the power of 67 years for stellar mass black holes, to 10 to the power of 100 years for the largest supermassive black holes. When the last black holes evaporate, the universe will contain only the extremely low energy photons and other particles produced by Hawking radiation. Dispersed through an enormously expanded space at a temperature approaching absolute zero. This is the heat death of the universe, the state of maximum entropy from which no further work can be extracted and no further events of macroscopic significance can occur. These timescales are almost unimaginably long. 10 to the power of 100 years is a number with 100 digits. The current age of the universe is approximately 1.38 times 10 to the power of 10 years, a number with 11 digits. The difference between the current age of the universe and the timescale for the last black hole to evaporate is as dramatic as the difference between a single second and the current age of the universe, multiplied by itself. The future of the universe is almost inconceivably long relative to the past, but this ultimate fate lies so far in the future that it is essentially meaningless from any human perspective. For all practical purposes, the universe is in its early youth. It has been forming stars for about 10 billion years and will continue forming them for perhaps 1,000 times that long. The Sun itself has about 5 billion years of main sequence life remaining. The universe is full of stars and planets and ongoing processes of extraordinary complexity and variety. We exist in the spring of the cosmic year. The pale blue dot is a photograph taken by the Voyager 1 spacecraft on February 14th, 1990, at the suggestion of the astronomer and author Carl Sagan. At that point, Voyager 1 was about 6 billion kilometers from the Sun, having completed its survey of the outer solar system. Sagan persuaded NASA to turn the spacecraft's cameras back toward the inner solar system and take a family portrait of the planets. In the resulting images, Earth appears as a tiny point of light, less than a single pixel in size, barely distinguishable from the noise, embedded in a ray of scattered sunlight. Sagan wrote about this image in 1994 with language that has since become one of the most celebrated passages in scientific literature. He wrote that Earth is a mote of dust suspended in a sunbeam, that all of human history, all of human joy and suffering and achievement and cruelty and love has taken place on this pale blue dot, that our planet is a lonely speck in the great enveloping cosmic dark. He wrote that we have an obligation to deal more kindly with one another and to preserve the pale blue dot, the only home we have ever known. The photograph and Sagan's meditation on it has become a touchstone for the scientific and humanistic perspective on our place in the cosmos. It communicates in a single image what all the numbers and all the distances and all the facts we have discussed tonight are pointing toward, that the universe is vast and ancient and indifferent to our concerns, and that our world is small and fragile and precious. That is not a reason for despair. It is a reason for wonder and for gratitude and for care. The universe did not need to produce consciousness. It did not need to produce beings capable of measuring the cosmic microwave background and detecting gravitational waves and imaging black holes and writing poetry and composing music and loving each other. That it did, at least once, and at least this corner of itself, is extraordinary. The atoms of the universe, following the laws of physics, for 8 billion years, produced this moment, this room, this resting body, this quiet. The universe is not obligated to make sense to you, but much of it does when examined with careful instruments and patient mathematics. The universe is not obligated to be beautiful. but it is, in its structure and its history and its laws, extraordinarily beautiful. And the universe is not obligated to have produced you, but it did, and you are here in the middle of all of it, at rest. Let every muscle that is still holding tension release now. Let your face be completely soft. Let your jaw hang slightly. Let your shoulders drop. Let your hands be open and still. Let your breathing be slow and automatic and barely conscious. The universe is 8 billion years old. The stars are in their courses. The galaxies are turning. The cosmic microwave background is arriving from every direction at 2.725 Kelvin. Dark energy is gently accelerating the expansion of space, and you are here on the pale blue dot, warm and still and breathing in the middle of a night that the universe has been patiently preparing for 13.8 billion years. You are made of the universe. You are the universe, briefly awake and aware of itself, now resting. Let it rest. Let it sleep. The stars will still be burning when you wake. There is more to carry into sleep. The universe is deep and patient and full of extraordinary things. Let its story continue a little longer, gently as you drift. The speed of light is 299,700,458 meters per second exactly. This is not an approximation. The meter is now defined in terms of the speed of light, so the speed of light in a vacuum is exactly this value by definition. Light travels approximately 30 centimeters, about a foot, in 1 nanosecond. It circles the Earth about 7.5 times per second. It travels from the Earth to the Moon in 1.3 seconds. It takes about 8 minutes and 20 seconds to reach the Earth from the Sun. It takes 4 years and 3 months to reach us from the nearest star. The impossibility of exceeding the speed of light is not a technological limitation or an engineering challenge. It is a fundamental feature of space-time. As an object with mass is accelerated, its energy increases, and the additional energy contributes to its inertia, making it harder to accelerate further. At speeds approaching the speed of light, the energy required to continue accelerating increases without limit. An infinite amount of energy would be required to reach the speed of light itself. The speed of light is therefore an absolute limit, a barrier that cannot be approached by any massive object, regardless of how advanced the technology. This is not a speculative extrapolation from current physics. It is among the most thoroughly tested predictions of special relativity. What does this mean for interstellar travel? The nearest star system, Alpha Centauri, is 4.37 light-years away, at the fastest speed a conventional spacecraft has achieved, about 250 kilometers per second for the Parker Solar Probe at its closest approach to the Sun. The journey would take about 5,000 years, even at a hypothetical 10% of the speed of light. An extraordinary engineering achievement, the journey would take about 44 years. At 99% of the speed of light, relativistic time dilation would compress the journey to only about 6 years from the traveler's perspective, though 44 years would still pass on Earth. These are engineering challenges of a magnitude that makes even the greatest achievements of human history seem small, but they are not forbidden by physics in the way that exceeding the speed of light is. Space-time, the four-dimensional fabric that general relativity describes, is not an abstract mathematical construct. It is physically real, and it behaves in ways that experiments have directly confirmed. The GPE satellites orbiting Earth provide daily proof that both special and general relativistic effects on clocks are real, measurable, and important for practical technology. Gravitational wave detectors directly measure the stretching and squeezing of space-time as gravitational waves pass through. The bending of light by gravity, first confirmed in 1919, is routinely used by astronomers to study distant galaxies through gravitational lensing. Space-time is not the passive stage on which physics occurs. It is an active participant, bending and rippling and expanding in response to the energy and matter within it. The twin paradox is a famous thought experiment in special relativity. Suppose one twin stays on Earth while the other travels at high speed to a distant star and returns. When the traveling twin returns, less time has passed for the traveler than for the stay-at-home twin. The traveler is younger. This is not a paradox in the logical sense. The twins have followed different paths through space-time, and the one who accelerated and decelerated experienced a shorter proper time. This effect has been directly confirmed in laboratory experiments using precise atomic clocks. Clocks flown on aircraft at high speeds return slightly behind identical clocks left on the ground. Muons produced by cosmic rays in the upper atmosphere travel at close to the speed of light and reach the Earth's surface in greater numbers than would be expected without time dilation, because from their frame of reference, the distance to the ground is contracted, and from our frame of reference, their lifetimes are extended by time dilation. Gamma-ray bursts are the most energetic individual explosions in the universe. They are brief, intense flashes of gamma radiation that are detected from random directions in the sky at the rate of about 1 or 2 per day. They come in 2 varieties: short gamma-ray bursts lasting less than 2 seconds, which are thought to be produced by the merger of 2 neutron stars, or a neutron star and a black hole, and long gamma-ray bursts lasting from seconds to minutes, which are thought to be produced by the collapse of extremely massive stars in events called hypernovae or collapsars. A gamma-ray burst can release as much energy in a few seconds as the sun will radiate in its entire 10 billion year lifetime, concentrated in a beam of gamma radiation far more intense than anything else in the universe. If a gamma-ray burst were to occur within the Milky Way and be directed at Earth, the resulting radiation could strip away the ozone layer and severely damage life. Fortunately, the rate of gamma-ray bursts in mature spiral galaxies like ours is very low, and the probability of such an event occurring and being directed at us in the foreseeable future is very small. The Hubble Space Telescope, launched in April 1990, has been one of the most scientifically productive instruments in the history of astronomy. From its orbit above Earth's atmosphere, where it is free from the blurring effect of atmospheric turbulence, Hubble has imaged everything from planets in our solar system to galaxies near the edge of the observable universe. Its images of stellar nurseries, like the Pillars of Creation in the Eagle Nebula, of colliding galaxies, of planetary nebulae, and of distant galaxy clusters, have become some of the most recognizable scientific images in history. The Hubble Deep Field images, taken by staring at blank patches of sky for long periods, revealed the extraordinary number of galaxies in the universe and provided a key dataset for understanding how galaxies form and evolve over cosmic time. Hubble has also made fundamental scientific contributions beyond beautiful images. It measured the Hubble constant, the rate of expansion of the universe, with sufficient precision to constrain cosmological models and eventually contribute to the tension between different measurements of this parameter that is currently one of the puzzles of modern cosmology. It detected the atmospheres of exoplanets using transit spectroscopy. It measured the masses of supermassive black holes through the kinematics of stars and gas near galactic centers. It contributed to the discovery of the accelerating expansion of the universe. And it has continued operating for more than 35 years, far beyond its originally planned 15-year mission, with periodic servicing missions by space shuttle astronauts extending and improving its capabilities multiple times. The James Webb Space Telescope, launched on December 25, 2021, and operational from mid-2022, has taken the tradition of deep space observation to a new level. G-WEST is a large infrared telescope, collecting about 7 times more light than Hubble and operating at longer wavelengths, where the earliest and most distant galaxies, whose light has been redshifted into the infrared by the expansion of the universe, are best detected. Its first science images, released in July 2022, immediately set new records for the depth and clarity of cosmological observations. Among GWEST's most dramatic findings in its first years of operation was the discovery of massive, fully formed galaxies at extremely high redshifts, corresponding to a time when the universe was only 500 to 700 million years old. These galaxies are far more massive and far more numerous than theoretical models had predicted, suggesting that galaxy formation in the early universe was more efficient than understood. GWEST has also studied the atmospheres of exoplanets in unprecedented detail, detecting carbon dioxide, water vapor, sulfur dioxide, and other molecules in planetary atmospheres. And it has imaged nearby stellar nurseries with sufficient resolution to reveal individual young stars and their protoplanetary disks in star-forming regions like the Orion Nebula with a clarity that previous telescopes could not approach. Neutrinos are among the most abundant particles in the universe, and also among the most ghostly. They are produced in nuclear reactions in the Sun, in supernovae, in nuclear reactors, and in cosmic ray interactions with the atmosphere. The Sun produces about 70 billion neutrinos per square centimeter per second at the Earth's surface. Right now, 70 billion solar neutrinos are passing through every square centimeter of your body every second. They pass through you without stopping, without interacting, without your knowledge. They pass through the entire Earth, from pole to pole, as if it barely existed. The entire planet is almost transparent to neutrinos. This transparency is because neutrinos interact only through the weak nuclear force and gravity, both of which have very small cross-sections at the energies of solar neutrinos. To have a 50% chance of stopping a solar neutrino, you would need a wall of lead about 1 light-year thick. The universe is pervaded by neutrinos from every nuclear reaction that has ever occurred, as well as relic neutrinos from the Big Bang that have been cooling for 13.8 billion years and now fill space at a temperature of about 95 Kelvin, slightly cooler than the cosmic microwave background. Cosmic rays are high-energy particles, mostly protons and atomic nuclei, that arrive at Earth from all directions in space at continuous rates. Their energies span an enormous range, from particles with energies comparable to those produced in laboratory particle accelerators up to ultra-high energy cosmic rays with energies 1,000,000 times higher than anything achievable at CERN. Though these extreme energy particles are extraordinarily rare, the sources of cosmic rays are not fully known. Lower energy cosmic rays are thought to be accelerated by supernova shocks in the Milky Way. The highest energy cosmic rays are thought to come from extragalactic sources, possibly active galactic nuclei or gamma-ray burst afterglows. Cosmic rays continuously create secondary particles in Earth's upper atmosphere, including muons that reach the surface and contribute to background radiation at Earth's surface and to radiation doses for aircraft passengers and crew. Let your breathing be slow and steady. In and out, the universe is full of particles passing through you right now, neutrinos from the sun, neutrinos from every supernova that has ever occurred, cosmic ray muons from the upper atmosphere, photons of light, the ever-present gravitons of gravitational fields. You are immersed in the universe, not separate from it. The boundary between you and the universe is permeable in every direction, and through all of it, you are at rest. The sun and the earth exist in a relationship of extraordinary interdependence. The sun provides the energy that drives almost all of Earth's biological and meteorological systems. Photosynthesis, which converts sunlight into chemical energy, is the foundation of virtually all food chains on Earth. The water cycle, which drives weather and replenishes rivers and lakes, is powered by solar energy that evaporates water from the ocean surface. The temperature of Earth's surface is maintained at life-compatible levels by the balance between absorbed solar radiation and the thermal radiation emitted by the planet. The sun also influences Earth through its magnetic field and the solar wind, a continuous stream of charged particles flowing outward from the corona. The solar wind shapes the magnetosphere of the Earth, the region of space dominated by the Earth's magnetic field, compressing it on the sunward side and stretching it into a long tail on the night side. Periodic disturbances in the solar wind, caused by coronal mass ejections and solar flares, compress the magnetosphere and drive currents that produce aurora at the poles and can interfere with satellite communications and power grids. The protection of the magnetosphere from the solar wind is essential for the long-term habitability of Earth, because without it, the solar wind would gradually strip away the atmosphere. The sun is about 4.6 billion years old, just under halfway through its main sequence lifetime. It is a perfectly ordinary star, classified as a G-type main sequence star or yellow dwarf, residing in the outer region of one of the minor spiral arms of the Milky Way. There are hundreds of billions of stars like it in the Milky Way alone. The sun's relative ordinariness, its lack of any extreme property that would make it special or unusual among stars, is in some sense reassuring. It suggests that the conditions that allowed life to evolve on Earth, the right type of star, the right orbital distance, the right amount of time, might not be unique to this solar system. Gravitational lensing, the bending of light by the gravity of massive objects, is one of the most powerful tools available to cosmologists and has a remarkable range of applications. Strong gravitational lensing produced by galaxy clusters creates arcs, multiple images, and rings of background sources that can be seen in deep telescope images. Weak gravitational lensing, the slight statistical distortion of the shapes of millions of background galaxies by the mass distribution of intervening structure, is used to map the dark matter distribution on large scales. Microlensing, the transient brightening of a background star as a compact object passes in front of it, is used to search for dark matter in the form of compact objects, to discover exoplanets, and to study stellar populations in distant galaxies. The Bullet Cluster, a system of two colliding galaxy clusters about 3.7 billion light-years from Earth, provides one of the most convincing direct pieces of evidence for dark matter. When the two clusters collided, the hot gas of the clusters, which makes up most of the ordinary matter, slowed down due to electromagnetic interactions between the gas clouds and accumulated near the center of the collision. But the dark matter halos of the two clusters, which do not interact electromagnetically, passed through each other with minimal interaction. Like two clouds of smoke passing through each other, gravitational lensing maps show the mass concentrated in two separate regions corresponding to the dark matter halos, while X-ray observations show the hot gas between them. The spatial separation of the mass as traced by lensing from the ordinary matter as traced by X-rays is direct evidence that most of the mass in the clusters is in a form that does not interact electromagnetically, i.e. dark matter. The anthropic principle in its various forms addresses the relationship between the existence of observers and the properties of the universe they observe. The weak anthropic principle, as we touched on earlier, states simply that we can only observe conditions in the universe that permit our existence. The strong anthropic principle makes the more controversial claim that the universe must have properties that permit the existence of observers, either as a logical necessity or by some deeper reason not yet understood. Between these lies a spectrum of positions with varying degrees of explanatory power and philosophical acceptability. One of the most striking applications of the anthropic principle concerns the triple alpha process in stellar nucleosynthesis. Carbon is produced when 3 helium nuclei combine in the core of a red giant star. This reaction proceeds through an intermediate state involving 2 helium nuclei and then the capture of a third via a resonance in the carbon-12 nucleus that makes the reaction proceed much more efficiently than it would without the resonance. In 1953, Fred Hoyle predicted the existence of this resonance on the grounds that carbon is abundant in the universe, and therefore this reaction must be efficient, and the resonance must exist. The resonance was subsequently found experimentally, exactly where Hoyle had predicted. The existence of carbon-based life, of which Hoyle was an example, was used to predict a property of nuclear physics that was then confirmed in the laboratory. The many-worlds interpretation of quantum mechanics proposed by Hugh Everett III in 1957 is one of several interpretations of the formalism of quantum theory. In the standard Copenhagen interpretation, a quantum measurement causes the wave function of the measured system to collapse to a specific outcome, chosen probabilistically according to the quantum probabilities. In the many worlds interpretation, there is no collapse. Instead, at each quantum event, the universe branches into separate versions, each corresponding to a different possible outcome of the quantum measurement. All outcomes occur, but in different branches of the wave function that do not subsequently interact. In the many worlds picture, there is no true randomness. All quantum outcomes occur with certainty, but in different branches. The many worlds interpretation is mathematically elegant, avoiding the need for the ad hoc postulate of wave function collapse, but it has the apparently extravagant consequence that the universe is constantly branching into an enormous number of parallel versions of itself. Whether these branches are real in any meaningful sense, whether the other branches can be detected or accessed, and how the probabilities of quantum mechanics emerge from a deterministic branching process are questions that remain actively debated. The many worlds interpretation is not a fringe view. It is taken seriously by many leading physicists and philosophers of physics, and it has implications for the anthropic principle, since in a many worlds universe, every possible quantum history occurs, making the existence of observers inevitable in some branches. The arrow of time, the fact that time appears to flow only in one direction from past to future, is deeply puzzling from a fundamental physics perspective. The laws of physics at the microscopic level, whether classical mechanics, electromagnetism, or quantum mechanics, are time-symmetric. They work the same way whether time runs forward or backward. Yet macroscopic processes are clearly not time-symmetric. A dropped glass shatters. The pieces do not spontaneously assemble back into a glass. Heat flows from hot objects to cold ones, but not in reverse. Order becomes disorder, but disorder does not spontaneously become order. The resolution of this apparent paradox lies in entropy and the second law of thermodynamics. In the direction of time we call the future, entropy increases. In the direction we call the past, entropy was lower. The asymmetry of time is the asymmetry of entropy, and the reason entropy was lower in the past is ultimately traced back to the low entropy initial state of the universe at the Big Bang. The Big Bang started the universe in a state of extraordinarily low entropy, and everything since has been the inexorable increase of entropy from that special initial condition. The arrow of time is the arrow of entropy increase, and the arrow of entropy increase points away from the Big Bang. Let your breathing be quiet and regular. The entropy of your body is low relative to its surroundings, maintained by the continuous input of chemical energy from food, which is itself the product of photosynthesis and the solar energy driving it. Your body is a temporary, local decrease in entropy maintained by the flow of solar energy through the biosphere. When you sleep, your body continues to maintain this low entropy state, though at a reduced metabolic rate. Your breathing slows, your heart beats steadily. The chemical gradients that sustain your cells are maintained. The universe permits you this extraordinary, improbable, temporary structure of organized matter and energy, and tonight it is at rest. Carl Sagan wrote in his book, The Pale Blue Dot, consider again that dot. That's here. That's home. That's us. On it, everyone you love, everyone you know, everyone you ever heard of, every human being who ever was, lived out their lives. the aggregate of our joy and suffering, thousands of confident religions, ideologies, and economic doctrines, every hunter and forager, every hero and coward, every creator and destroyer of civilization, every king and peasant, every young couple in love, every mother and father, hopeful child, inventor and explorer, every teacher of morals, every corrupt politician, every superstar, every supreme leader, every saint and sinner in the history of our species lived there, on a mote of dust suspended in a sunbeam. Sagan continued, "Our planet is a lonely speck in the great enveloping cosmic dark. In our obscurity and all this vastness, there is no hint that help will come from elsewhere to save us from ourselves. The Earth is the only world known so far to harbor life. There is nowhere else, at least in the near future, to which our species could migrate. Visit, yes, settle, not yet. Like it or not, for the moment, the Earth is where we make our stand." He concluded, "It has been said that astronomy is a humbling and character-building experience. There is perhaps no better demonstration of the folly of human conceits than this distant image of our tiny world. To me, it underscores our responsibility to deal more kindly with one another and to preserve and cherish the pale blue dot, the only home we've ever known." These words, written 30 years ago, have only grown more resonant. The universe is 13.8 billion years old. It is 93 billion light years across, and its observable extent. It contains 2 trillion galaxies. It will continue for an effective eternity. And in all of that, the only confirmed place where anything has cared about anything, where love exists, where art exists, where science exists, where one being can be concerned for the well-being of another, is the pale blue dot. That is not a source of despair. That is the most extraordinary fact in the universe. That matter, after 13.8 billion years of physics and chemistry and stellar evolution and planetary formation and biological evolution, can become aware of itself, can look out at the universe and ask why it exists, can feel awe and compassion and curiosity and love, is the deepest mystery and the most remarkable fact we know. The universe did not have to do this. There is no law of physics that requires consciousness. It happened here, on this small planet, around this ordinary star, in this unremarkable corner of one ordinary galaxy among 2 trillion, and that it happened at all, even once, is enough to make the universe worth the 13. 8 billion years it took to get here. You are the universe aware of itself, resting tonight. Every quantum field that Higgs predicted is permeating your body right now, giving mass to your particles. The gravitational field of the Earth is holding you in place with the same equations Einstein wrote down in 1915. The light from the sun, produced by quantum tunneling 8 minutes ago, has warmed the air around you. The atoms of your body were forged in stellar interiors billions of years before the Earth formed. Let every remaining tension in your body release now. Let your face be completely soft. Let your breathing be so slow and quiet you barely notice it. You are safe. You are supported. The planet is holding you. The galaxy is turning slowly around the galactic center at 230 kilometers per second, which you cannot feel. The universe is expanding at its dark energy-driven rate, which you cannot feel. The cosmic microwave background is passing through you in all directions at 2.725 Kelvin, which you cannot feel. The 70 billion solar neutrinos per square centimeter per second are passing through you, which you cannot feel. The universe is going about its ancient, patient business, and you are resting in the middle of it. The most complex, most improbable, most extraordinary thing in the known universe, a conscious mind, is choosing to be still tonight, to breathe slowly, to let the thoughts quiet, to sleep. Sleep now. The universe has 8 billion years of momentum behind it and needs nothing from you tonight. Let it carry you. Let the ancient light of the cosmic microwave background surround you. Let the gravity of the earth hold you gently. Let the oxygen produced by billions of years of photosynthesis fill your lungs with each quiet breath. Let the stars burn. Let the galaxies turn. Let the dark energy push the universe gently outward in every direction. And let yourself rest in the middle of all of it. The Voyager 1 spacecraft is currently about 24 billion kilometers from the Sun, traveling at about 17 kilometers per second relative to the Sun, the fastest any human-made object has ever moved. It crossed the heliopause in 2012, the boundary where the solar wind yields to the interstellar medium, and entered true interstellar space. It is now moving through the medium between the stars, measuring the plasma density and the magnetic field of the interstellar space around it, sending those measurements back to Earth on radio waves that take about 22 hours to arrive. On board Voyager 1 is the Golden Record, a 12-inch gold-plated copper disc containing sounds and images selected to portray the diversity of life and culture on Earth. It contains greetings in 55 languages, music from many cultures and periods including Bach and Beethoven and Chuck Berry and Azerbaijani folk music and Senegalese percussion and Native American chants, natural sounds of the Earth, including rain and wind and surf and thunder, and the songs of birds and whales, brainwaves, and photographs representing life on Earth. It was assembled under the guidance of Carl Sagan and Anne Druyan, among others. The record is intended for any extraterrestrial intelligence that might someday intercept the spacecraft, but it also serves as a message from humanity to the future and a reminder of what is most worth preserving about life on this world. Voyager 1 will continue traveling in roughly its current direction for the foreseeable future. In about 40,000 years, it will pass within about 1.7 light years of the star Gliese 445 and the constellation Camelopardalis, a closer approach than any currently planned spacecraft will make. In 300,000 years, it will have traveled to the distance of Sirius. In 40 million years, it will begin to enter the Oort cloud, the outermost region of the solar system. The Golden Record will survive on board, unchanged, for billions of years in the vacuum of space, a message in a bottle thrown into an ocean whose shores may never be found. The concept of what it means to understand the universe is one that scientists and philosophers have wrestled with throughout history. When Galileo turned a telescope on Jupiter and saw the 4 large moons orbiting it in 1610, he understood something new and profound, that not everything in the sky orbits the Earth. That simple observation broke the conceptual foundation of the geocentric model of the universe that had dominated Western thought for 2,000 years. When Newton derived the law of universal gravitation in the 1680s, and showed that the same force that made an apple fall from a tree also kept the moon in orbit and the planets around the sun. He unified the physics of the terrestrial and the celestial in a way that had been unimaginable before. When Maxwell unified electricity, magnetism, and light into a single theory of electromagnetism in the 1860s, he revealed that three seemingly separate phenomena were aspects of a single underlying reality. When Einstein showed in 1905 that space and time are not absolute but relative, and in 1915 that gravity is the curvature of space-time, he transformed our understanding of the physical framework of the universe at the deepest level. Each of these revolutions in understanding produced a reaction among those who encountered the new ideas for the first time that combined the uncomfortable feeling of having one's previous certainties overturned with the exhilarating experience of seeing a larger and more beautiful truth revealed. The history of physics is the history of the universe revealing itself to be larger, stranger, and more deeply structured than any previous generation had suspected. There is no reason to believe this process is complete. Let your thoughts be like clouds drifting across a clear sky. You do not need to hold on to any of them. Let them form and dissolve. Let the facts about the universe that we have discussed tonight drift past without needing to be grasped or remembered. The universe does not need to be understood to be rested in. The equations that govern it operate whether or not any conscious being knows them. The stars burn whether or not anyone watches. The cosmic microwave background fills space whether or not any telescope detects it. And gravity holds you gently to the surface of the earth whether or not you think about the equations of general relativity. You are held, you are supported, you are safe. In a universe of almost incomprehensible scale and age, on a planet of almost incomprehensible richness and variety, in a room that is warm and quiet, you are resting. The universe spent 13.8 billion years producing this moment. It produced the hydrogen and helium of the Big Bang, and the stars that fused them into heavier elements, and the supernovae that scattered those elements, and the nebula that collapsed to form the solar system, and the Earth that formed from that nebula, and the ocean that formed on the Earth, and the chemistry that gave rise to life in that ocean, and the 3.5 billion years of evolution that produced complex multicellular organisms, and the further evolution that produced vertebrates, and mammals and primates and hominids and modern humans, and the specific sequence of events that produced you, in this specific time and place, breathing quietly in this specific room. All of that to get here, to this moment, to this breath, to this rest. The universe is complete in each moment. The stars that are burning right now across 93 billion light years of space are each complete in their burning. The molecular clouds collapsing into new stars are complete in their collapsing. The supernovae scattering their elements are complete in their scattering. The quasars blazing at the universe's edge are complete in their blazing. And you, lying still, breathing slowly, drifting toward sleep, are complete in your resting. This is the universe at rest. Let it be enough. Let your breathing be so slow now that you can barely feel it. Each breath in, gentle and full. Each breath out, long and complete. With each breath out, let a little more of the day's activity fall away. Let the thoughts that are still trying to form dissolve before they finish forming. Let the body be still. Let the mind be quiet. The universe will be here when you wake. The galaxies will still be turning. The Milky Way will have rotated by a negligible fraction of a degree. The Andromeda Galaxy will be imperceptibly closer. The cosmic microwave background will be infinitesimally cooler by the fraction of expansion that has occurred overnight. The stars will have burned a tiny bit more of their hydrogen, and Voyager 1 will be about 1.5 million kilometers farther from the sun than it is right now, sailing silently through the interstellar medium with its golden record, carrying a message from a small blue world that once looked up at the stars and wondered, "Let sleep come. You have earned this rest. The universe has earned this moment of your rest. Everything is in its place. Everything is as it should be. The laws of physics are holding. The forces are balanced. The planet is orbiting. The galaxy is turning. The universe is expanding. And you are, for this quiet night, at peace in the middle of all of it. Good night."